Welcome. In this session, we'll explore a Lagrange function for a simple constrained optimization problem that we've explored in a previous lecture. Let's recall this problem. And the problem was, we stated it as objective function 1 that has a vector argument was simply the squared norm of the argument, and we said that the property function for this was a 1 form minus 1, 1 times the argument plus 3. If we take the Lagrange function definition from the previous class, we can directly write this down. So the Lagrange function would be a function that has a vector argument and a scalar argument, and that is we write down the objective function, so that is W transpose W, and then we add the Lagrange multiplier times the property function. So that would be minus 1, 1 times the vector argument of the objective plus 3. So now we have the Lagrange function. Next, we need to find the Lagrange equations, and we begin by finding the derivatives, which are 1 forms. And that would be the partial derivative of this function with respect to the vector argument will be, when we differentiate this term with respect to W, that will be 2 times W transpose. And when we differentiate this term with respect to W, that will be mu times minus 1, 1. I'm going to commute those, and I'll say that's plus minus 1, 1 times mu, and then the other term is mu times 3, and the partial derivative of that with respect to W is 0, so we'll omit it. Next, we differentiate the Lagrange function with respect to the Lagrange multiplier, and that will be the derivative of this with respect to mu is 0, so we just leave that, and the derivative of this property with respect to mu is the property, so we just write down the property function, which is minus 1, 1 times the vector argument plus 3. Now, what I want to do is I want to set these equal to 0. And I observe that what I see is here I have a W and a mu. Here I have a W and the mu is missing, but I kind of could put that in. So let's try writing this as a matrix vector equation. So what we want is let's write W and mu, and let's leave a little space over here. You are writing this down, aren't you? Yeah. Okay, so now the question is, what are the matrix and the vectors that we have? So here, when we set that equal to 0, the right-hand side will be the 0 vector, and I'll write those as 2 components. Here, well, I can imagine that there's an identity function there, right? So I could say that that is 2 times W, so that is 2 times the identity times W, plus this will be, when I've transposed that, that will be that'll be the vector minus 1, 1 times mu equals 0. Let's just cross-check that. Let's take that 1 form and transpose that. And that would be 2 times the identity times W, plus, and when we transpose that, it is minus 1, 1 times mu, because when we transpose a scalar, it's a scalar. And then when we transpose this term, the partial derivative of the Lagrange function with respect to mu transposed will equal, now we transpose those, and that will be W transpose times minus 1, 1, plus 3. And, oh, this is a scalar, and so remember that the product of a one form and a vector is a scalar, and so we can commute those, so that actually is the same as minus 1, 1 times W plus 3. Okay, so now what that tells me is when I set that equal to 0, that means that the right-hand side will be minus 3, and this will be minus 1, 1, minus 1, 1 times W plus 0 times mu. And so I've written down the Lagrange equation, and now the Lagrange equation turns out to be a problem of 3 equations in 3 unknowns, which is readily solvable. And so I can say, well, there's only one solution to this, and that one solution is the stationary point. And when I work this out, and I really encourage you to do that because you can do it you can quickly do it just by looking at this bottom row, is that what we'll find is that the optimal argument is 1.5 minus 1.5. And once we know that optimal argument, we can put it into one of these equations, and we can find that the optimal Lagrange multiplier for this problem is 3.